Good evening, everyone. Welcome back to this live session 2. I hope everyone can hear me.
Yes, sir.
Okay, and can you see my screen? Okay, I can see the answers in chat box. So welcome back to this live session 2. We had this live session in week 1 also. So we are back with live session 2, and we'll start this session at 7:05. We will give 1 more minute for anybody who wants to join this meeting. Then we will start the meeting, start this session. Uh, So, how is this week for every one of you? Is this fine? I could see a lot of people joining now. How many of us are in the meeting? Something around 18 or 19. Okay. So, in case you have any queries, you can also write in the chat box, or you can unmute yourself and ask in the middle. I will appreciate your questions. Okay, it's 7:05, and let's start. People are still joining. Okay. Uh, so once again, good evening to all of you present here in this live session 2. So this is a live session of physics of renewable energy system. This is a NPTEL course run this year for 12 week, and this course is taught by Professor Amrish Chandra. He's with Department of Physics, IIT Kharagpur, and this course is taken up by me, that is Rohit. I am a research scholar in IIT Bombay, and I am also a PMRF grantee. Okay. So we will have how I have planned this session. We will have some recap. Then we will shift to some questions, some conceptual questions, some trick question I will ask to you. You can answer, or I will give you the answers. What are perfect answers for this trick question, or what else you can think. So I want that you think in a broad sense, not some narrow, like you just have to complete this course only. You can think of some narrow broad sense. You can add some knowledge from your side also, like sir, this can also be think on these lines. So yeah, I will appreciate that. Okay, for revision of the concepts, for the last week, which passed on I think 30th of July, we were actually discussing different concepts of solar irradiation, some albedo concepts, what are the different albedo values, scattering, how much sunlight is received by the earth, and various other concepts. So based on that, we determined that the solar constant value is approximately a constant. In a period, it's a constant, and its value is 1367 watt per meter square. Based on that, we solved a numerical in which we estimated irradiance value for 1st of June. Remember, for the last question we had 1st of June and 31st of December. So I want that you again go through this and calculate it for 11 June. So for 11 June, what we see that the number of days passed. So number of days passed, how do we count the number of days? it is counted since 1st of Jan. So since 1st of Jan we have 31 days in January, 28 days in Feb, 31 in March, and similarly 11 days in June. So it total out to be 162 days, and this 162 days is similarly put into the formula here, and we put the values of solar constant from here. Let me take a pointer. We take the value from solar constant from here, put here, and after putting all these values we calculate it to be 1327.41 watt per meter square for 11th of June. So this is just simple numerical, but this numerical is simple, but if you learn this concept you can apply it to calculate irradiance or irradiation value for any particular day. Similarly, you can also calculate for 28th of February, like we have calculated for 11 June. For 28th Feb, what do you think what it should be? Number of days passed should be 31 plus 28, that is around 59 days. Similarly, you put the 59, n equal to 59 here, ISC value, calculate, it should be something around 1380 or 90 maybe. So you can put it and calculate at yourself. So this is all for the revision of last week. Any questions from these concepts? Anyone want to ask? Oh, someone has written in the chat box 1413. Yeah, it's correct. Okay. So any questions regarding these last concepts, last week concepts? Anyone want to ask some questions or has any doubts or suggestion? Okay, so we will move to the next part. My slides are visible. Okay. So for the first question is basically these are questions from previous run of this course, assignment 2. So this question is actually repeated. DSSC solar cells falls under which category of photovoltaic classifications? So from previous week we knew that DSSC, that is dye sensitized solar cell, basically falls under the third generation of solar cells. So this is a third generation solar cell. So the correct answer for this is C. And actually this dye sensitized solar cell was a very what you say, revolutionary concept in solar cell design actually. It was developed by Professor Michael Grezel and Dr. Brian O'Regan. So these two scientists actually developed this concept, and actually these dye sensitized solar cells have very high efficiency. They are good efficient solar cells, and they basically used a dye instead of some substrate. Use a dye, and based on this dye they some redox reaction takes place, and this dye sensitized solar cell works. So we will learn more about it during the week 2 in which Professor Amrish Chandra has also taught about some functioning of these dye sensitized solar cells. So these comes under the third generation solar cell. What is the first generation solar cell? These are basically polycrystalline or monocrystalline solar cells, silicon based solar cells. Second generation solar cells are amorphous silicon based solar cells, or you can say organic carbon based solar cells also. Third is dye sensitized solar cells, and fourth generation solar cells are the latest one, that is perovskite. Okay, perovskite cells are actually much recent phenomena, and we could see a lot of research going on in these perovskite based solar cells. So we will know more about them in the upcoming slides also. Okay, now moving to the next questions. The next question is, evacuated tube collectors are basically we compare the evacuated tube collectors with flat plate collectors for water heating. So the options are, evacuated tube collectors are more efficient than flat plate collectors, evacuated tube collectors are less efficient, both of them have same efficiency, or none of the above. So if we see these three options, these two options are actually matching, just they have used the word more or less. Both of them have same efficiency. This can also be possible. So let's see what are evacuated tube collectors and flat plate tube collectors. So in evacuated tube collectors we have a cylindrical tube, actually a cylindrical tube of glass, an outer glass covering and an inner glass covering. This inner glass covering, wait, someone wants to join. Okay. So evacuated tube collector has a outer glass covering and an inner cylindrical glass covering. This inner glass covering has some selective coating on it. Selective coating, actually what does selective coating does? Selective coatings, actually what do we need in a solar cell or something, solar heater? We need a high absorptivity and we need less emissivity. So this selective coating is actually high on absorptivity and less on emissivity. So it absorbs the solar radiation which comes and emits very less. Okay, so that's how it is designed in a cylindrical form. Why it is cylindrical? It's a cylindrical because cylindrical, or you say curvature shaped, because at any instant, any direction sun rays are coming, it falls perpendicular to it. You see, perpendicular, perpendicular, perpendicular. But if it would have been a flat, then solar ray falling at some angle, this is not perpendicular. So some component, only a vertical component will be absorbed with much high efficiency, this will be absorbed with much lesser efficiency. That's why the evacuated tube collectors were designed for a better performance. So you know which of these are more efficient. Similar, based on this design, evacuated tube collectors are more efficient than flat plate collectors. Flat plate collectors are simple tubes. These are simple tubes, water flows into it, and there is some glass coating here. The rays are absorbed in it, and this it heats the water flowing into it, or you can say fluid flowing into it. Now there is a trick question here. Which system is more efficient in converting sunlight, solar photovoltaic system or solar thermal system? When I say solar photovoltaic system, these are basically solar cells that converts direct electricity, sunlight to direct electricity. And in solar thermal system, it converts sunlight to heat, that we can see here. It actually converts sunlight to heat, and that heat is actually used to raise the temperature of water or thermal fluid that is flowing inside it. Okay, so according to these two, which do you think is more efficient in converting sunlight, solar photovoltaic system or solar thermal system? Any one of you? Am I audible? Okay. So any one of you can answer? Any guesses? Okay, let me tell it for you. This is a simple concept. Like in solar, what do we see in solar? photovoltaic systems. In solar photovoltaic system, the maximum energy conversion goes to 20 to 25%. This is the maximum value which we have been achieved with help of 4th generation solar cells. But in solar thermal system, this efficiency can go high as 45% or even more. Generally it is 45%, 30 to 45%, 30 to 45%. This is so in terms of conversion of sunlight, the solar thermal systems are actually more efficient than solar photovoltaic system. So why do we use solar photovoltaic system? Then we could use the solar thermal system only. There is a catch actually. In solar photovoltaic system, we actually directly get the electricity, sunlight to electricity. But in solar thermal systems, we don't get electricity directly. We get sunlight, then heat. Then heat has to be used to raise the temperature of water to convert it to steam. Then again that steam will go through turbine and it will again convert to electricity. So a whole lot of system adds up here, which actually pulls down this efficiency to less than 10% for conversion of electricity. So that's why direct conversion of solar sunlight to electricity is preferred through solar photovoltaic systems. And in this course also you will read some some heliostat based system or solar thermal power plants also in week 3 or week 4, where you will get to know about how solar thermal systems are used to produce electricity also. So we have still people joining. I would request all of you to join on time so that we can start the session, and I don't want any one of you to miss this lecture actually. These are some conceptual questions where we discuss the concepts, some questions from previous assignment. So I always think that it should be much useful for you, much helpful, and we have a great fruitful discussion based on this. Okay. Uh, so in between we have a concept called band gap. We will discuss about it later. We'll go move to question 3 because questions are actually need to be discussed. So for question 3, the question is general chemical formula for typical perovskite material is. See, I was talking about 4th generation solar cell. Now here is the 4th generation solar cell material, perovskite material. Okay, what we know of perovskite, these were actually discovered in Ural mountains. Ural mountains are basically in Russia. These are on the borders of Russia or some Caucasian region, you say. Ural mountains are there. There they discovered compound, a material or matter, you can say perovskite material. So what this perovskite material has, this has a shape of AbO3. Okay, this chemical formula, this is in the form of this chemical formula. And perovskites are basically calcium titanium oxide, CaTiO3. So you see this actually fits into it. Ca, Ti, B is Ti, and O3 is here. This also has the shape of some octahedron shape, octahedron lattice. You can note it down, octahedron lattice. And it actually can't be said one material. It is a group of material which follow this whole chemical formula AbO3. So these are perovskite based material. So these are some new concepts in solar cell technology, and these are actually embedded in between P and N junction, N and P junction, and actually these materials actually help in increasing the efficiency of solar photovoltaic cell, and efficiency as high as 28% has been reported because of usage of these materials. So you can see how much importance are these materials. So if you see some recent trends in research paper, you can see a exponential growth in research articles on this perovskite based materials is there. So if anyone wants to do some research in this solar cell arena, or wants to develop some high efficiency solar cell, then similar a better scope is using this perovskite based material and doing research on these. There are a lot to be done, and there are a lot you can add to the knowledge gap here. Okay. Question 4. So question 4, the question 4 is the width of energy bands in solid materials. There are 4 options. It increases with band order number, decreases with band order number, or it remains same, or none of the options are true. Okay. So first we will understand what are the energy bands. Energy bands, we see that energy bands are actually electron energy levels, and that forms a continuous energy variation. You can't say anything as a band. You have to have a electron energy level, and it has a continuous energy variation. That's how bands are formed. So we will see more about this band here. So bands are actually how does this band come? This band actually comes when you see an electron in an orbit. This is an atom, this is the nucleus, and if this is the electron, so you can't say with exact possibility that electron will be found here only in this orbit only. Electrons actually travel, actually jumps, comes back. So it is basically represented in the form of probability. That's how it looks like. The probability of finding the electron in the this is actually distributed like this, and we say that with this much probability this electron will be there in this orbit. So this probability distribution is actually represented by a Schrodinger function, Schrodinger wave equation, and that Schrodinger wave equation is solved for that eigen and is solved for some k values of this bands, and an eigen value is obtained. So for a single solution, 2 eigen values are obtained. So that's how these. So we can have various solutions. So for all these solutions, similarly, two eigen values were obtained. So these all eigen values are actually, what are these eigen values? These are actually the bands in the atoms. These represent the band in the atoms. So that's how the bands are defined. Bands are basically the energy levels on which the electrons, there is a possibility of finding the electrons, and which has a continuous variation of energy. Okay. So in metals, what we see that these bands actually overlap. The valence band actually overlaps with the conduction band. That's how the electron actually jumps from the valence band to conduction band. That's why metals we see are highly conductive. For semiconductor, there is some gap in between two, but given the excitation, this electrons can jump from valence band to conduction band. In insulator, what happens? This band gap is too high, or you can say too large. So it is very difficult for electrons to jump from valence band to conduction band. That's why insulators doesn't conduct electricity. So for if you see this band gap for semiconductor is actually in between 0.1 to 3, and for insulator it is actually greater than 3 electron volt. And these band gap are actually energy difference between the top of the valence band, that is this, and the bottom of conduction band. That's how this band gap is defined. Okay. So for this, the width of energy bands in the solid materials increases with band number, decreases with band order number, remains same with the band order number. So for a width of band, energy bands is actually defined for a particular atom, for a particular electron. So it always remains same with the band order number. So the correct answer is C. One more concept is there. So there is a concept of free electron model. This is a theory which actually explains the whole band gap thing, and bands are actually, because of this free electron model, this actually explains all the various basic phenomena, like how the electrical conductivity occurs, how the thermal conductivity occurs. So this free electron model actually explains all these. So what is free electron model? So in simple terms, I will in layman terms I want to show you what is a free electron model. Free electron models actually says that there are lattices on which the metal atoms are situated at some specific points like corners or body center, and in between these spaces there are electrons, and these electrons are mobile. They can move from one lattice to other or adjacent lattice. That's how the conduction or flow of current or flow of heat actually occurs. This is the free electron model. Here also there is a trick question, or you can say not a trick question, there is a simple question like can you name one method of formation of PN junction semiconductor diode? There are many methods of formation of PN junction semiconductor. Like the first one is alloyed junction, in which what we do, we put a N type semiconductor here, like silicon. We put some aluminum here, and actually we heat up it to the eutectic temperature. That's how a layer of aluminum is formed here that behaves as a p-type semiconductor. That's how PN junction is formed. Second one is we pass gases consisting of p-type semiconductors over this, so a layer is deposited. That's how this is formed. Or a lithographic technique can also be used. So lithographic technique can also be used to form this p-type semiconductor. So there are various processes that can be utilized to form PN junction semiconductor. Now question 5. Which of the following properties of solar cell is actually utilized for industrial application? So for solar cell, let me see if anyone wants to join. Yeah. Okay. There's some people are joining late. Okay, I will ask them to join. So people who are joining late, I would request you all guys to please join in between the. I think one more person wants to join. Let me see. Yeah. Okay. So people who are joining late, I would request them all to join in starting of 5 minutes, so that disturbance to the class is least, and we can go through all these concepts and discuss them with full dedication. Okay. Actually I also want that you take part in discussion, general discussion also, so that more transfer of knowledge could take place. Now the question 5. So anybody has question before this? So we discussed this 1 2 3 4. Anyone has any questions? You can also write in the chat box. I could read the chat box and answer accordingly. Okay, no questions. Then let me move ahead and discuss the question 5. So the question 5 is, which of the following properties of solar cell is utilized for industrial application? So we knew that solar cells, basically what are solar cells? Solar cells are devices that convert sunlight to direct electricity. So similarly, if this has to be used for industrial application, this has to be reliable, because anything which is not reliable, it cannot be a commercial product. So when we go for industrial application, it has to be a commercial product. That's why reliability is very much necessary. And what if we have very low efficiency, like 1% or 2%? Why do we use something which has a very low efficiency when we have some alternate products with very high efficiency available? Like if the solar cell doesn't give a very high efficiency, then we can always move to the solar thermal system, which gives a high efficiency of 30 to 45%. So high efficiency is also a requirement for industrial application. Even if it is not industrial application, any commercial application, like for household also, you need to have a high efficient product. Okay. And long term stability is basically you don't have any physical degradation, you don't have any chemical degradation. So long term stability is also a requirement. So what we can see here, that all the three options are actually correct. So the correct answer for this question is answer D. And let me ask you a question here, like what else would you like to see in a solar cell apart from this: reliability, efficiency, long term stability? In solar cell, actually apart from these are actually very much important characteristics of solar cell that can be utilized for industrial application. But apart from this, there are some other features also that are required, like the solar cells should, the material which is used for fabricating these solar cells should be readily available. Okay, the operation and maintenance should be easy. Okay. So what happens if some of the parts of solar cell are actually not working? So we can easily replace them if the materials are readily available. For industrial application or for commercial application, we need to have a skilled manpower also. So skilled manpower is also requirement. What if everything is known, but skilled technician is not available to change this? So skilled manpower is also requirement for any commercial application. Okay. Now moving to the question 6. The number of electrons above the Fermi level at absolute zero is. Now if you see the questions, there are two parts: number of electrons and the Fermi level at absolute zero. Absolute zero, what is absolute zero? Absolute zero is minus 273 Kelvin. That's how it is defined. Sorry, 0 Kelvin. Okay, not minus 273. 273 is actually 0 degree. So if we 273 Kelvin is 0 degree. So if we minus 273 from here, minus 273 degree Celsius is absolute zero. Why this concept of absolute zero is very important? Because at absolute zero, all the entropy, that is randomness in the molecule, disappears actually at absolute zero. So you can say that all the metals actually behaves as a superconductor at this temperature, at absolute zero. Superconductor means there are no resistivity to flow of electrons. So whatever currents you through at one end of this metal here, it will receive the same as the second end. That's how this superconductivity is useful for day-to-day phenomena. So scientists are basically going for those metals which can show superconductivity at much higher temperature, not at absolute zero, because absolute zero is very difficult to achieve, very difficult. How can you achieve a minus 273 degrees Celsius? So we don't have such system which can regularly maintain minus 273 degrees Celsius at all times. So that's how, why scientists are actually searching for some materials which can show superconductivity at minus 20, minus 50 or something. Okay. So coming over to the question, we have number of electrons, Fermi level at absolute zero. We got the concept of absolute zero from here. Now we will understand the concept of Fermi levels. Fermi level is the energy level which is occupied by the electron orbital at temperature equals to 0 degree. Okay. So in simple terms, actually, when temperature is 0 Kelvin, the energy level up to which the electrons move is called the Fermi level. So in simple terms, like this is the conduction band, valence band through which the electrons move, and this is the conduction band. So there must be a Fermi level in between these two. This Fermi level is the level up to which this electron can travel. This valence band electron can travel from here. That's how a Fermi level is obtained. Fermi level actually varies with different types of semiconductor. With p semiconductor and n semiconductor, these Fermi level for different bands can vary. For n-type semiconductors are actually loaded with electrons, so these Fermi levels are actually nearby these n-type semiconductors. For p-type semiconductors are actually more rich in holes, so this Fermi level will be somewhat away from this surface of valence band. Okay. So number of electrons above the Fermi level at absolute zero. From the definition we knew that the electrons can only travel up to Fermi level only. So above the Fermi level at absolute zero, there can be no electrons, exactly zero. So as per the concept, this is a typical conceptual question. So applying the concept of Fermi level, the answer is exactly zero. And for a unbiased PN junction, so PN junction where there is no applied voltage, we will learn about bias and unbiased, reverse bias and forward bias PN junction in the lecture also. I will discuss it in the upcoming slides also. So for unbiased PN junction, this Fermi level is actually constant throughout the semiconductor. Now moving over to the question 7. What is the difference between intrinsic type semiconductor and extrinsic type semiconductor? This is the question I have taken from the slides. So make you understand what are the intrinsic type semiconductor and what are the extrinsic type semiconductors. If we see the intrinsic type semiconductors have basically number of holes equal to number of electrons. These are pure semiconductor which are found in nature. So remember this, intrinsic type semiconductors are actually pure semiconductors which are found in nature, like some examples are silicon, germanium, maybe indium also. I don't know indium is a semiconductor or not. There are many others also. So that's how intrinsic semiconductors is defined. And for extrinsic type semiconductors, what happens that these semiconductors, silicon, germanium, actually doped with pentavalent impurities. Okay, and trivalent impurities. When it is doped with pentavalent impurities, there are more electrons in it, so it behaves as n-type semiconductor. When it is doped with trivalent impurities, it has more holes in it, so it behaves as a p-type semiconductor. So these two n-type and p-types are basically extrinsic semiconductors, which are basically doped semiconductors. So you got to know the difference between intrinsic semiconductors and the extrinsic semiconductors. Intrinsic semiconductors are those semiconductors which are pure semiconductors in which number of holes and number of electrons are equal. In extrinsic semiconductors, we actually doped them with boron or some other atoms, or pentavalent or trivalent impurities. These pentavalent trivalent impurities are basically atoms. Pentavalent have 5 electrons, trivalent have 3 electrons, so one pair is available for sharing. Now moving over to the question 8. What happens to the depletion region when we apply reverse biased voltage to it? So here comes the bias, which I discussed in previous slide. So what happens to the depletion region? See, depletion region are charge devoid regions in between the semiconductors. If this is a p-type semiconductor, this is a n-type semiconductor, this is the depletion region. These are charge devoid regions where the holes and electrons are combined. Okay, and if we apply this reverse bias, what does reverse bias do? Reverse bias actually throws the carrier charge, actually forces the carrier charge away from it. Okay, so if this is plus, this is minus, this will actually repel the plus charge. So what happens, this, if depletion layer is this, like this, in the earlier we apply the reverse bias to it, it will move here and move this plus here. So that's why what happens, this layer actually grows. So if we apply a reverse bias voltage to it, the depletion region actually grows. So this is the correct answer. And by how much voltage it grows? So you can see a depletion region if has a initial bias voltage of V0 and we apply a reverse bias of voltage V, so the total depletion region will grow to V plus V0 into E. Okay. Now to the next question. So next question is basically a numerical. This is based on the concept of solar cell, which has been taught in the slides. So I picked a formula and put a numerical for you to know actually how much is the resistance of current. So what happens here, if this is a solar cell, sunlight strikes here. If sunlight strikes this solar cell, then it will convert sunlight to electricity. This electricity, there is some metal conductor placed here to these cells. This electricity flows through these conductors and collect in the bus bar. Okay, so what happens when sunlight strikes, some electricity is produced. This electricity is actually collected through these metal contacts to bus bar, and through bus bar it is taken out and flows through a load. Okay, so similarly anything, if it is metal, it will provide resistance to the path of current. So that's why we use metals which has very less resistivity or resistance to the flow of current, like silver, copper. In fact, we mostly use silver in solar cells, so that very less resistance can be offered to the flow of current. So if we are to calculate this, how much resistance is offered to the flow of current? So if we see a metal contact to the cell, that's how a cross section of solar cell looks like. This is the metal contact, this is N, this is P, so this is PN junction, the solar cell comes, the electron is generated, and this is taken out as an electric current. So if the height is h, width is w, L is the length, so the resistance to the flow of current is rho into L divided by W into H. This is the total resistance to the flow of current. So simple, this is a simple numerical in which we put the resistivity value here. Length is 0.3 divided by width 0.1, and similarly height is 0.1. So the total resistance comes out to be 5.16 into 10 to power minus 7 ohm. So mind it, this is for simple single conductor of 0.3 meter length. We can have tens of meters of length and hundreds of thousands of these metal contacts on the top, based on the how much area the solar cell covers. That's how this resistance adds up, and actually it provides a resistance to the flow of current. That's how this value needs to be calculated, and this needs to be minimized. So how can we minimize it? We can minimize it through decreasing the value of resistivity. So for decreasing the value of resistivity, what we can do, we can select some material which offers a very low resistivity to the flow of current. Okay, so that's all for today. We discussed in the slides. Let me again discuss it again for some people who joined late actually. So firstly, we discussed about the revision of concepts in the last week, in which we discussed about irradiation, solar constant, the way to calculate irradiance on the particular days like 11 June, 28th Feb. We use this formula to calculate the irradiation at 11 June. Similarly, you guys can do it for 28th Feb. We discussed the concept of DSSC solar cells, that is dye-sensitized based solar cells. These solar cells are actually third generation solar cells. The first generations are polycrystalline solar cells or monocrystalline silicon based solar cells. Second generations are amorphous silicon based solar cells. The third generation are dye-sensitized based solar cells, and the fourth generation solar cells are perovskite based solar cells. In question 2, we discussed evacuated tube collectors compared the evacuated tube collectors with flat plate collectors for water heating. We knew that evacuated tube collectors have some curved area, so that's why sunlight falling on the surface is actually normal at any point of time. So that's how it works, and the efficiency it provides is actually greater than the flat plate tube collectors, where the incident angle, if sunlight is falling at some incident angle, it doesn't transfer the whole heat to the surface. Only the sunlight which is falling normal to the surface actually transfers the heat. Then we discussed band gap. What are the band gaps for metals, for semiconductors and insulators? So we also discussed the concept of free electron models. Free electron model in which we have a lattice. The metal ions are actually occupied at the corners or some special position like body center, face centered, and in between the gaps electron occupy, and these electrons are actually mobile, so that it can move from one lattice to another lattice. In third question, we actually discussed the chemical formula of perovskite based materials. So perovskite material are basically, perovskite is nothing but calcium titanium oxide, and these are actually discovered in the Ural mountains, mountains situated nearby Russia. So a Russian scientist actually discovered this perovskite based material, and this perovskite based material are actually a recent phenomena, and said to be enhancing the increasing the efficiency of solar cell. So that's how much of the research is going on in the perovskite based materials. Then we discussed the width of energy bands. We discussed the energy bands. Energy bands are basically the electron energy levels that forms a continuous energy variation. Okay. Then we discussed the different methods of formation of p-n junction, in which one is alloyed junction, another is some form of gas which contains this n type semiconductor can be moved over a p type, so a deposition can occur, or lithography technique can be used. In question 5, we discussed the solar cell. What are the properties that are necessary for its application, industrial application? When we say industrial, it's commercial application. So it has to be reliable, it has to be higher efficiency, it has to be have long term stability, and so the answer is all of the above. Then we discussed the Fermi level. Fermi levels are actually electrons energy level which is occupied by electron at temperature equals to 0 Kelvin. So at temperature equals to 0 Kelvin, that is absolute 0, the electrons above the Fermi level are exactly 0. Okay. In question 7, we discussed the intrinsic and extrinsic type semiconductors, where intrinsic type semiconductors are basically pure semiconductors where number of holes are equal to number of electrons, and in extrinsic type semiconductors we doped the semiconductors with impurities, pentavalent or trivalent impurities, to make p type or n type semiconductor. In question 8, we discussed depletion region and applied reverse bias voltage to it to check what happens to the depletion region. We saw that depletion region actually increased, and the value is E into V plus V naught. In question 9, we solved a numerical in which we put the value of resistivity, length, width and height of metal contact and calculated the resistance. So this is over for today's live session, and I am open for interactions or any queries or doubts. So if you have any queries, you can also find me at this email. You can write me an email anytime, or you can always write it in discussion forum of the NPTEL course. So anybody has questions regarding this?
Sir, how this certification course will help us getting into renewable energy?
Okay. Okay. So you are asking that how this NPTEL certification course will help you in getting in renewable energy field. See,
Yes, sir.
see what I can say, that renewable energy is a very vast field. It doesn't only limit it to solar cell only. You will see wind also. You will see geothermal also. You will see bioenergy also. So I will say first you develop an interest toward this field. It's not that you only like solar energy. When you will learn about wind energy, you will say, this is the concept I wanted to learn. When you actually like the subject, you like a particular thing about the subject. So if you like solar energy, you go into solar energy, you learn the softwares. Okay, you learn the softwares
Yes, yes.
like PV Syst or something. See what industry people are demanding. So they are basically demanding most of the solar what you see in India in solar, most of the work is being carried out in solar cell basically, but solar cells are not manufactured in India, so installation work is going on. So learn about these, how these electrical connections are actually done to the solar cell. Okay. And talking about this certification, this actually you can present to the employer that yes, I know this field. So someone who is not having a certification in solar energy or renewable energy field, and someone who is having a certification in this renewable energy, and both have same levels of knowledge, and I am the employer, who do you think I will ask for job? Like I have this certification, you don't have this certification, and both of us have same knowledge, and we both go to employer. So who do you think has most chance of getting this job? One who has this certification, because the employer will know that he has been taught this course systematically, he knows this course very well. So that's how this course actually helps in getting you job. Okay.
Okay, yes, sir. But
Okay.
do we need any other certification course with this?
Yes, you will need to learn some softwares, and also you need to learn some electrical. Try to learn electrical MPPT type of thing, multi power point tracking, how the connections are done, bus bars, how different solar modules are connected. Okay,
Yes, sir. Thank you.
welcome. Any more questions?
No, sir.
Okay, no questions from your side. So I think let me ask question from my side then. So let us have an interaction, a simple formal or informal type of interaction. So most of you are actually students from colleges. Okay. So are you all guys from renewable energy systems, or you guys are doing engineering and MSc? I could see some. I could hear in previous week that some people said that I am doing MSc on something.
Um, MSc
Okay, you are from MSc.
electronics.
Okay, MSc in electronics. That's nice. Okay. Okay, Durgam Veer Bhadranath. He's saying that Veer Badrinath. Okay. Don't mind if I pronounce your name incorrect. Durgam. Okay. You are from engineering. Okay, nice. So, if you see, I am from this background, renewable energy system background. I've done my bachelor's from mechanical engineering. Then I moved to this renewable energy system because I like this field. Network issue. Can everybody hear me, or is there a network issue? Okay. So okay. Thank you, Prakash. Yeah, hearing. Okay. So I liked this field actually, but what I liked about this field, there are bioenergy. There is something called bioenergy. So I was much more interested in that bioenergy. But whole of renewable energy concept is very much fascinating because most of the world, all of the world, is moving towards a renewable. You know, our prime minister's push is for renewable. We will have some 300 or 400 gigawatt of energy from renewable by 2030. So that's a huge lot of potential. So you will see more and more companies coming into this field. So what do you think? 5 years earlier, there are hardly 2 or 3 companies in this field, but now in India, you see that a lot of companies. I can name 100 companies in this field. So 100 companies means 100 types of job opportunity, thousand of job opportunities. The main thing is that you learn this subject with whole heart. You know this subject. You know the intricacies. You know the skill. You don't go for only theoretical things, you also apply it. And what I will say, you group together and make companies. Government of India is providing so much of big loans, uh, to carry out some entrepreneurship type of ventures in this field. So I will always request you guys to go in this field only, entrepreneurship. Don't look for job, look for making company, look for selling products. Okay. uh, so in this week we discussed about solar photovoltaic cells. We also had a lecture 9 on solar thermal systems. We'll know more about it in upcoming lectures also. So I wish that you guys learn these concepts. These are very easy concepts, and you can grab it. You can actually apply it also. I would suggest that you try to build a PN junction diode by yourself. Try it. Try to build it. If the materials are not available, you can always try. Sir, the final exams are in MCQ or pen and paper written type. There will be some instructions available in announcement section in NPTEL for final exams, and those instructions will actually list out the points which will be applicable for the final exam. So basically the NPTEL course final exams are only MCQ types, or you can have some fill in the blanks type also. So this is main concept, but they can change also. You can wait for the announcement. Okay. So what I was there, that you try to learn these concepts. Okay. And I would appreciate if you would ask some questions also in this discussion. If anything is not understood by you, you can also ask it to me. So I think that's all for today, and we can end this meeting here. So if anyone has any query, he can always write email to me. He can ask it in the discussion forum also. So it was nice meeting you all guys. So that's all for this week. Okay.